How are we going to talk about strength? Well, this term correlation, and we're going to use the variable R for correlation. R is going to give us two of the three that we need. Remember, we need form, direction, strength, and then is there anything unusual? R will tell us the direction as well as the strength. So R must be a value between -1 and +1. The sign of R, whether it's positive or negative, will give us the direction. The closer R is to 1 and -1, the stronger it is. Again, remember, strength is basically saying how close are the dots to being perfectly on a straight line. So you can see in graph 6, the correlation is -0.99. Well, negative, yes, it's clearly going down as x gets larger, y gets smaller. So R is telling us it has a negative slope, or there is a negative association is the term we would use. 0.99 is very close to 1. It's almost as strong as it could possibly be. So we would say that graph 6 has a strong negative association. Any value between -1 and 1, if we see R, any value other than something between -1 and 1, it's a mistake. The other interesting thing about correlation is there are no units. It's not 1 mile per hour or -0.7 grams or 0.3 pounds. There is absolutely no units on correlation. It's just giving us a picture of what the scatter plot is looking at. Look what the scatter plot looks like. It's telling us, oh yeah, hey, these dots are really close to being on a straight line, as you can see here in graph 6, and they're negative, or the slope of the line that would fit these points the best would be a negative slope. This sentence, this saying up here, we're going to repeat over and over and over and over again. Correlation does not imply causation. So if we have a super strong correlation like 1 or -0.99 as in graph 6, it doesn't mean that the change in X is what's causing the change in Y. It could, but it doesn't necessarily mean that X is causing Y. And we will look in later chapters about how we can talk about causation. In this case, we can just say there's an association. There's a linear relationship between the two. As X gets larger, so does Y in a linear pattern. But it's not saying that X causes Y. And that's what this little cartoon is telling us up here. The little boy is saying, oh yeah, well, I had the remote and now it's in the TV. Well, correlation does not imply causation. It doesn't necessarily mean that I did it. So we need to remember that saying, correlation does not imply causation. How do we calculate correlation? Well, there is this crazy looking formula here. What we're going to do is take each individual X, subtract the mean of X, divide it by the standard deviation. Take each individual Y minus the mean of Y, divided by its standard deviation, and we're going to multiply those two values together. We're going to do that for each and every data point in the data set. And then we're going to find the sum of all those and then divide it by n-1. So what we would be doing is we would take each X value, so all these data points in here, we take each one of their X values, find the mean of all the X values, take each one of these points again and their Y values, and find the mean and standard deviation of Y, and find the mean and standard deviation of X. We should not have to actually calculate this formula by hand. We're gonna see technology is going to do this for us. So we are going to use our graphing calculator and have it calculate the correlation for us. But it's good to know where the formula comes from. And in the formula packet that we're going to use on the AP test, you will see this formula written out. Most of the time, though, they'll write it more compactly using the summation notation. So we would say R equals 1 over n-1. All that's really saying is, after you're done, divide it by 1 less than how many dots there are in the graph. X sub I means each individual X. So we take every single X value, subtract the mean, divided by the standard deviation. Do the same for y. Really what we're doing here, this should look pretty similar. Really what we're doing here is z-scores. Remember that z was x minus mu over sigma, or each individual, or the x value minus the mean divided by the standard deviation. Each x value minus its mean divided by the standard deviation. So we're finding the z-score for x and y, multiplying them together, and then doing that for every single point in the data set. Okay. Now, you can see the skull and crossbones here. There is some common mistakes made over and over in correlation. And one of them is saying, oh yeah, correlation is 1, therefore the size of your hand causes the amount of starburst chosen. Well, it could, but it's not necessarily the case. Okay. Correlation does not measure form. Remember, we need to talk about form, direction, strength, and like always, anything weird or unusual. Okay. Correlation does tell us direction and strength. It does not tell us form, nor does it tell us unusual. Unusual we'll get just visually by looking at the scatter plot. Form is coming up soon. So remember, correlation gives us 2 of the 4 things we need. It tells us the direction and the strength. So if I know that R equals 0.9, I can say, oh, it's positive because there's no negative sign in front. 0.9 means positive 0.9. And it's relatively strong because it's close to 1. The closer we get to 1 and -1, the stronger the relationship is. So if we had an R of -0.9, it is equally strong as positive 0.9. It's just a different direction. So again, R only can tell us direction and strength, but it cannot tell us form or identify any unusual relationships. Okay. Next, correlation is only used to describe linear relationships. If it's a quadratic or a cubic or exponential or a power, correlation does not describe that. Correlation is only used for linear relationships between 2 quantitative variables. And finally, the next caution is that correlation is not a resistant measure of strength. Remember that resistant means that you are strong, tough, you are unaffected by extreme observations. Anything that has to do with mean, any formula that uses X bar or Y bar or the mean of a data set will not be resistant. Think about your grade. If you have 100% in the class and you get a 0 on the final, your mean, your average grade is not resistant to that 0. It's certainly going to drop. So anything that involves mean is not a resistant measure.